So the Dirac Delta function, this crazy D, what does this mean? Well, this Dirac Delta function is a special function that enables us to evaluate sampled systems, or rather impulses. This Dirac Delta function is an impulse, okay, and it's an impulse at time equals 0. And at all other times, we get 0. But what do we get at this point at t equals 0? Well, in theory, what we get is an infinite magnitude. Okay, this tends off to infinity. However, when we want to do the maths, infinity becomes a little bit hard to handle. So often what we try and do is constrain this magnitude. And the way we constrain it is we give it a value that is essentially proportional to the width of the pulse. So if we said that this width was capital T, then this will be t over 2, and this will be minus t over 2. We say that the height of this is 1 divided by t. Now if we do that, if we were to integrate under this square pulse, if you like, then we say t over 2 dt, we would end up with the answer equal to 1. Okay, so if we integrate under this dt, we end up with a value of 1. Now, as we make this t smaller and smaller, then this would essentially make this value, or constrain this, or make this go bigger and bigger. So, but in essence, the key to the maths is when we integrate it, however infinitely small we make this period, this integral will always equal 1. Now, any time domain function can be represented by a series of complex exponentials, and the Dirac delta function is no different. We can say that the Dirac delta function is equal to the sum of 1 over t, and we say it's 1 over t because this is going to be the value of the magnitude of that particular component, e to the j omega nt. Okay, now if you look at the Fourier series equation, that is the Fourier series equation, and this here is our Fourier coefficient part. Okay, so there is a proof as to why that is 1 over t, and if you think about it, if you make small t equal 0, then this part is going to equal 1. Okay, and at all the other times, the magnitude section is going to be of size 0. So this is how we get this Cn term here. Now, why is that such a special function? Well, if we think that it's an infinite sum, remember this is minus infinity to plus infinity, this is an infinite sum of complex exponential, which means that in this impulse part here contains loads and loads and loads and loads, an infinite number of sinusoids, which is pretty radical. But what that enables us to do is, if we were to put this impulse into a system, so we go put an impulse in, okay, if we were to get an unchanged output, i.e. just a single pulse output and nothing else, then this is like saying x of n equals y of n. Okay, now if x of n equals y of n, then the transfer of this system, it's like saying it's multiplied by 1. And if we multiply it by 1, then the input equals the output, or rather the output equals the input. Therefore, the frequency ranges, or frequencies going in, must equal the frequencies coming out. So, multiply by 1, you would expect that, wouldn't you? Now, if we put an impulse in, then sometimes with our system we see multiple, particularly if it's a fed back system, we might see multiple tails here. Okay, now this is what we call the impulse response, because it's the response to a Dirac impulse. And essentially what we're seeing here is this is affected, this magnitude of this Dirac function. Think about this, these are all Dirac functions, but they're shifted. This is -1, this is -2, blah 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 blah, and they're all scaled. So a shifted and scaled output like this indicates that there is some kind of feedback system or feed-forward system going on. And essentially, if we take away frequency components from this, then we're going to get maybe smaller values. We might even see in some cases larger values. You know, if we add back in frequency components, we get like a feedback system. We have to be careful with that though, because we can get, you know, this can continually grow and we get oscillations out of control. But essentially, this is what we're doing when we're feeding in this Dirac delta function into our system. That's how and why we get these impulse responses.